To facilitate the bookkeeping needed for the different types of program discontinuities that I mentioned, Exokernel maintains the PE data structure on behalf of each library operating system. So for example, this PE data structure corresponds to this library operating system. This PE data structure corresponds to this library operating system. And the PE data structure contains the entry points in the library operating system for dealing with the different kinds of program discontinuities. For example, exceptions that are thrown by the currently executing process has a specific entry point in the library operating system. And similarly, external interrupts are going to be handled by interrupt handlers that have specific entry points in the library operating system. And a process may make system calls, and if it makes system calls, there is a protected entry context, which is the entry point in a library operating system for system calls that are made by the currently running process that belongs to that specific library operating system. This last entry may correspond to the addressing context, that is the location of the handler for page fault service in the library operating system. So in a nutshell, this PE data structure that is unique for every library operating system contains the handler entry points for different types of events that are fielded by Exokernel. In this sense, the PE and the associated Exokernel action of calling the appropriate handler entry point when a particular event is triggered is very similar to the event handler mechanism that we discussed in the SPIN operating system. In addition to the PE data structure, we already mentioned the software TLB that Exokernel maintains on behalf of every operating system. So this is a software TLB for OS 1, software TLB for OS 2, and these are what are called the guaranteed mappings. Or in other words, I mentioned that on a context switch, Exokernel, when it goes from one operating system to another, it saves the current TLB in the hardware TLB, in the software TLB that is associated with this particular operating system. And here is where this entry point is important. This actually is specifying to Exokernel the set of guaranteed mappings that a particular library operating system wants Exokernel to maintain on its behalf every time it is scheduled. And that's the set of TLB entries that are dumped into the software TLB data structure at the point of a context switch. Not all of the hardware TLB entries, but only the entries that have been guaranteed to be kept on behalf of a particular operating system are dumped into the software TLB data structure. And those are the ones that will be repopulated into the hardware TLB when the same operating system is scheduled on the hardware. I mentioned an external interrupt as another source of discontinuity for the currently executing process. Well, note that an external interrupt may not always be for the currently scheduled operating system. It may be for some other operating system. Maybe this operating system scheduled a disk I/O and the disk I/O got complete, and that interrupt that came in to Exokernel is on behalf of this operating system and not the process that is currently executing on the CPU for this operating system. Exokernel has to have a way of associating the interrupt that is coming in with the correct operating system which is expecting it. Downloading code into the kernel, which I mentioned as one of the mechanisms that Exokernel provides, allows first-level interrupt handling on behalf of a library operating system.